Mark Showalter. He's a senior research astronomer at the SETI Institute. He enjoyed science-themed toys as a child, and he worked to save money to buy a telescope, which he had in his early college years. He pursued an education in astronomy, astrophysics, space, and planetary sciences after seeing the images of Jupiter sent back from the Voyager 2 space mission. He received an MS and PhD from Cornell in 1985. He's the principal investigator of NASA's planetary data systems, a co-investigator on the Cassini-Huygens mission to Saturn, and he works closely with teams on the team with the New Horizons space mission. In 1990, using 10-year-old Voyager 2 data, he discovered the innermost moon of Saturn, which is now named Pan. He discovered Jupiter's faint ring system and characterized the details caused by the impact of comet Shoemaker-Levy 9, which you may remember. It was 1994. In 2011, he began a Hubble observing program focused on Pluto, which led to the discoveries of 2 tiny moons. A Mars-crossing asteroid number 18499 Showalter is also named after him. And when you go home, look him up on Wikipedia. This is just a fractional list. There's way more on it than that. New Horizons flyby of Pluto. I was so happy that we're having this talk tonight. Pluto and its moons were just dots in the sky. All of that changed on July 14th last year when the New Horizons spacecraft flew past Pluto and provided our first close-up look of these distant worlds. The spacecraft performed flawlessly, sent images of remarkable landscape, and they're still being downloaded back to Earth. In this lecture, Mark Showalter, a co-investigator on the New Horizons mission, will describe how he discovered 2 of Pluto's moons and will recount the inside story of the latest scientific results from Pluto. Join me in welcoming Mark Showalter. Thank you.
Thank you, everybody. It's great to be here tonight. Thank you, Linda, for that nice introduction. As you may imagine, I've been using this slide in a number of my talks for actually a couple of years now. July 14th, 2015 is or was the big day. I started using this slide back when we were talking about Pluto, the encounter that was about to happen in 2014 and in early 2015 when I was giving those lectures. And the first thing I'd like to do as an order of business is say, I'm sick and tired of artist renderings, so let's actually look at the real thing. So Pluto did not let us down. It's a just gorgeous landscape, incredible rich detail picked up by our spacecraft. And what I'd like to do tonight is talk a little bit about the story of the mission, the story of how I became a Pluto scientist, which was kind of by accident, frankly. And then we'll get to the latest results and even a little bit of 3D that you may be preparing for if you know you've seen the glasses that were on your chairs. So. Let's go back in time and just kind of get this story started. Back in, as we were assembling the spacecraft, this is what it looks like. It is, you can see 2 humans for reference scale. We always say, I don't know why we always do this analogy, but it always seems to work. It's the size of a baby grand piano. This is a small spacecraft by NASA standards. The Cassini mission that I also work on is an orbiter at Saturn. The Cassini spacecraft is about the size of a small bus. It's a much larger spacecraft, several tons, whereas this would fit very comfortably in the foreground right in front of the screen there in front of you. There's a reason why you want a spacecraft to be small and light if you're sending it to Pluto. So what we did is we took this spacecraft and we put it on a very big rocket, the largest we could, an Atlas V, and on January 19th, 2006, it was launched from the Cape and on its way to Pluto. It was sent away from Earth as the fastest object ever sent from Earth. It crossed the orbit of the moon in about 9 hours. Now, if some of you are old enough to remember the Apollo flybys, or the Apollo landings, took the Apollo spacecraft about 3 days to get from the Earth to the moon and then 3 days back. This was 9 hours. So that's what you do by putting a small spacecraft on a big rocket. In just so there was an interesting thing that happened just in the short period after we left Earth and before we got to Jupiter, which was our first pit stop on the way, the International Astronomical Union, you've heard this story, I'm sure, changed its mind about what exactly a planet is. So here's the definition of a planet. I got this off of just Webster's, I think. A celestial body orbiting in an elliptical orbit around a star. What could be simpler than that? That's a planet. And then that was August 23rd, 2006. One day later, a big asterisk got added by the International Astronomical Union, and also has sufficient mass to assume hydrostatic equilibrium and has cleared the neighborhood around its orbit. P.S. A dwarf planet is not a planet. So at that time, Pluto was demoted, and we still, of course, everybody still talks about that, and everybody still has opinions about that. To my way of thinking, saying, well, I don't mind the term dwarf planet at all. Pluto is a very small planet. I do a lot of work on the giant planets, and by comparison, Pluto is much smaller than the Earth's moon even. So calling it a dwarf planet, that just makes perfect sense. We have giant planets, we have terrestrial planets, we have double planets, we have all kinds of planets. So a dwarf planet is fine, but a dwarf planet is not a planet. To me, is equivalent as saying this. And, you know, I just think there's a certain absurdity to it. At a certain point, my feeling is there aren't 9 planets, there aren't 10 planets, there are hundreds and hundreds of planets. It's basically the generic word, and until you put dwarf or giant or terrestrial or something else, modifier in front of it, it really doesn't mean very much. But the IAU didn't ask my opinion, and so here we are. Anyway, it's still open to debate. You can call Pluto a planet as far as I'm concerned. Dwarf planet is fine. I'm just happy to be able to talk about it the way we can at this point in time, frankly. All right, so after that little detour into politics, here we are. It was only 13 months later that we reached the planet Jupiter. We did a flyby, and this was a really great opportunity for us all to test out our instruments. So let me give you a little quick introduction to our instrument package. As I said, it's a very small spacecraft, and it's got a very limited set of instruments. However, it does have a very, very fine camera called LORRI. It is unlike many of the cameras that we send on much larger spacecraft. It's a very simple camera. It is black and white. It has no filter wheels. It doesn't do color at all. To do color, we actually have a different instrument called RALPH that does 4 colors, and when you see a color image of Pluto, what you're actually seeing is a detailed image taken by LORRI and then a slightly lower resolution image taken by RALPH, and the two of them overlaid. And that gives you a very nice rendition of color, and your eye is fooled by the fact that the color isn't at quite the level of detail that the black and white image is. We also get infrared and ultraviolet. We have a radio science, and that's of course also for communication with the Earth. We have some charged particle instruments as well, but I won't be talking about them too much. All right, so here we are at Jupiter, and this was a beautiful image that was done actually as a combination of several of the instruments that I've spoken about, using the color and the black and white to show Jupiter, and the great, one of the white spots, the red spot was actually sort of on the other side of the planet. Here's Io, large inner moon of Jupiter, and you can see that little blue glint, that is actually from a different instrument, and that's showing a volcano erupting on Io that just happened to be erupting as we were flying by in 2006. So this gives you a taste of what our instrument package can do. On the left, this is LORRI. This is the camera that just does black and white. But notice the incredible detail in here. It's a very high resolution CCD. Then we have at lower resolution in real visual color, the same picture of Io. This is taken by what's called MVIC. It's part of the RALPH package that gives us our color, but at lower resolution. And then finally, we can go a little further into the infrared, and we can actually see heat glowing. The volcano, this big volcano called Tvashtar, which luckily just happened to be erupting as we did the flyby, is of course a very hot spot. So even though it's on the dark side of the planet, it's glowing with heat. And in fact, you can see some other hot spots. These are volcanic calderas on the dark side of Io, not in sunlight at all, but emanating their thermal heat, and we're picking that up. So that's how it all works together, and we get a more complete picture of Io as a result. We had a very lucky circumstance on the Jupiter flyby. This is the only existing movie of a volcano erupting on a place other than Earth. And it happened by total accident because as I said, we didn't know this major volcanic eruption was going to be happening at the time we got to Jupiter. And nobody had thought, well, let's put in a movie sequence because, you know, what would you be taking a movie of? It's just Io. But I, in fact, actually, as the planner of the Jovian ring observations, there's a very faint Jovian ring, which is actually going across this image, and it's too faint to see here. And I decided it would be cool just to have a Kodak moment. We would take a sequence of images when I knew that the Jovian ring and Io would be in the same field of view. And I estimated that that would look kind of cool. It turns out the ring was too faint for us to see. But that sequence of images, about 5 images taken 5 minutes apart, is what became our only existing movie. So a lucky shot that we didn't plan on. That's how serendipity works sometimes. All right, so moving on from Jupiter. Let me see. Sir, I am sorry I forgot to begin by hitting record. So I'm going to, I apologize for that, but that means your recording is going to be a little bit limited. All right, let's.
Being ejected from Io.
It is basically small. I mean, it's small dust particles, and there's actually a liquid interior of Io. These are icy objects, believe it or not, although they don't look that way to us. There's a lot of sulfur in the interior of Io as well, but it's sort of like geysers on Earth, probably, in the sense that there's water and there's sulfur, and it would smell bad if you could actually go out there and smell it. I don't know that number, so sorry about that. Typical temperatures at Jupiter are in the sort of liquid nitrogen range, like 70, 80 K, somewhere in there, I think. Okay, so there's something very valuable about flying by Jupiter, which is you notice this trajectory, which now took us on to Pluto, has a little bend in it. We saved about 1.5 to 2 years in flight time getting to Pluto because of that Jupiter flyby. So not only did it give us a chance to test out our instruments and all our procedures for planning out observations and executing them, but it got us to Pluto faster. So that 3 billion mile trip took 9 years when it would otherwise have taken 11 or 12. All right, but my work was done. I was involved in the Jupiter flyby, and that was the end of my role. I was an expert, am an expert on the Jovian ring and the small satellites, and that was the science that I worked on in that part of the mission. And I said, great work, team, go to Pluto and have a great time, and I'll watch from afar. But then there was something else that happened that kind of was my quirky entry to the Pluto world of Pluto science, which is that right around the time of launch, some colleagues of mine on the team, Hal Weaver was the leader of the group, discovered that Pluto, now we already knew about Pluto and Charon, and these are two these are two similar sized objects that are orbiting one another essentially. They are overexposed in this image taken by the Hubble telescope, and what Hal and his colleagues discovered is that there were two dinky little moons also orbiting Pluto and Charon. They were given the names Nix and Hydra. So this was very interesting to me. I had some long discussions with the colleagues on the team, and we started thinking about, well, you know, what we see elsewhere in the solar system often are things like this. When you have a small satellite, often you have a slender ring of dust that is in the same orbit. The idea is that a meteoroid, some particle comes in, hits the small moon, raises a cloud of dust. That material escapes from the surface, but then spreads out around the central planet and creates a slender ring. This is Anthe. It's about a 1 kilometer object, a small moon orbiting Saturn. Saturn would be off over by the Golden Gate Bridge somewhere. But as you can see, there's this dust ring in the orbit of Anthe. And so we started thinking, dinky satellites, you often have dust rings. Maybe Pluto has rings. Let me show you another example. This was some work I did back around 2003 to 2006. We discovered a little moon called Mab orbiting Uranus here. And if you look very closely in this heavily processed image, you can see that there's a ring. That's a faint ring of dust that shares its orbit with Mab. Stuff is coming off of Mab and then spreading out around Uranus. Same idea. So the idea is if we have Nix and Hydra, we could have little rings. And actually my colleagues on the team had already done a search. But the trouble is, you can kind of see here, this is what a hypothetical Hydra ring would look like, or a Nix ring over here. The problem is that there's a huge amount of glare because these objects are very, very faint compared to Pluto and Charon. And so we had this great idea about how to use the Hubble telescope to find the rings of Pluto to a level much more sensitive than this search had been done. And that was our idea. And let me show it to you how it works. Basically, let's go back. Sorry about that. So our idea, go back. So our idea was to take images of Pluto and Charon, and we could vastly overexpose Pluto and Charon by factors of 50 or 100 if we wanted to. And we would take two sets of images, one in which the space telescope is oriented a certain way, as shown on the left, and then we would rotate the entire spacecraft 90 degrees, wait for Charon to come around so it was about the same place on the CCD, on the telescope, relative to Pluto, and take another image. So we get two images with these big glare patterns around Pluto and Charon, but the ring would be rotated. Everything else would be the same in the optics of the camera, but the ring would be rotated. And that's the idea, that you then could overlay those images, subtract, and the glare would cancel out, and you would be left behind with a positive image of the ring and a negative image of the ring. And that would be a very sensitive test, 100 times more sensitive than they had been able to do so far. So we were very proud of this proposal. We patted ourselves on the back. We submitted it to the Space Telescope Science Institute. It went through review. And of course, how could it fail? But this is the message that we got back a few months later. Let me just highlight my favorite sentence. Your proposal was graded in the 4th quartile of proposals in your panel, with the 1st quartile being the top proposals before the panel. Not only did they put us at the 4th quartile, but they felt they needed to explain to us what it meant to be in the 4th quartile. I mean, I could only take comfort at this moment that there was no 5th quartile, but anyway, this is where the story should have ended, and I would have licked my wounds and gone home. Because, I mean, even though we did have a good idea, I think the panel didn't understand it, the panel didn't think it was important, whatever. So we had this weird little ace in the hole, though, which was that there was a spacecraft, I'm back to artist rendering, sorry, but there's a spacecraft on its way to Pluto and Charon and Nix and Hydra. And the team planners were very, very interested if we were going to encounter this as the Pluto system, or this as the Pluto system. And a ring, that's dust, that's potential hazards, that's lots of little things that can poke holes in your spacecraft. You don't want that to happen. So there was a mission at stake regarding whether there might be a ring around Pluto. There were people who really cared a lot. And so certain people on the New Horizons team talked to certain people at the Space Telescope Science Institute. This doesn't happen to me normally. But for whatever reason, here we are a couple months later, and we are actually looking at our 4th quartile data set that we never thought we would see. Now here we are, you can see that Pluto and Charon, as I described, are sort of on a diagonal. They're heavily overexposed, but this would be a hypothetical Nix ring in this image. Now it's really kind of a mess. You see all those stars passing through the field of view. Pluto at this time is basically in front of the center of the galaxy, so it's a very, very dense star field. So my heart kind of sank. How are you going to deal with looking for rings in that kind of a data set? But the thing you could take advantage of is the fact that the stars are moving and everything else is standing still. It's actually the opposite, but of course the Hubble telescope is very, very good at tracking a moving object. So it kept Pluto dead still, fixed in our field of view as the stars streamed by. And that meant we could do some magic and clean it up. And so there we did, and there you can see Nix and Hydra quite beautifully. And does anybody, maybe people in the front, I told you should sit in the front, see anything else that might be interesting? There's a lot of snow. These are called hot pixels. These appear in any CCD. You learn to ignore them. You learn where they are. They are all cataloged. But there was one extra object. Do people in the front see it? It's not off to the left, actually. It's right there, a little dot, and there I'll circle it. And actually let me zoom in even, I can make it a little closer for you. So if everybody sees it now, I hope. This looks like a moon. It's got a point spread function. It's a fuzzy, it's not just a single hot pixel. It's not like this little snowflake or that little snowflake, which is a hot pixel. This is sort of fuzzy. It's got the right shape to be a point object that's passed through the optics of the Hubble camera. And I was pretty sure, this was only hours after I'd seen the data, that we had the discovery of a moon. I called up Alan Stern, our project manager, our project principal investigator, on the phone, interrupted in the middle of a Mexican restaurant, and told him what we were looking at. We were very excited, but we had to wait. The trouble is one little detection doesn't prove that it's a moon. It could be a background object, an asteroid, who knows. But we actually had more data coming, and so it was about a week later that we actually had our second set of opportunities to look for this object, and it had moved. It had moved relative to Nix in the right direction as everything's going around that way, and that was what convinced us that we had a moon of Pluto. So that got named P4 because we didn't have a name for it at the time. But the following year, everybody was thinking after this discovery, oh my gosh, if we didn't know there's another P4 is there, what else don't we know about in the Pluto system? This is really a concern. And so we had a much more extensive observation period with the Space Telescope the following year. And I will skip over a whole lot of data processing, but one day in July of the following year, 2012, I processed a bunch of images. It's a 3 set of images. Each of these is like a 45-minute total exposure. And here's P4 as we expected, and Hydra and Nix. And maybe, does everybody see that there's actually another moon there? I'll draw a circle around that one. So that was a discovery of, guess what, P5. Let's call it P5. So we had 2 moons to deal with, and now we were really concerned about what the heck might be going on in the Pluto system. But by the way, we did have a naming campaign. We let the public decide what to name these 2 little moons, and they got named Kerberos and Styx, and that was a great fun. The names of Pluto system moons come out of Greek mythology about the underworld. So Pluto is, of course, also known as, I'm sorry, I'm drawing a blank. Hades, thank you. The god of the underworld, Pluto in the Latin, Hades in the Greek. Styx is the river that surrounds the underworld. Nix is the goddess of the night. Hydra is the weird creature with sneaky heads and things that guards the gates. And Kerberos is the 3-headed dog who is, I guess, Hades' favorite pet. I don't know. Anyway, it's lots of fun. I'm sorry? And Charon, of course, yes, is the boatsman who ferries the souls of the dead into the underworld. All right, so this is our family. This is where we're going. This is our target, and target is a scary word because target means we're going at it, but who knows what it's got coming at us. So here is the kind of the way we're flying through the system. 14 kilometers a second, that's very, very fast, 10 miles per second, roughly speaking. And we're going through that plane, and if there's something in our pathway, results won't be pretty. So here's our concern, and let's now show you. So there was a whole study that then we embarked upon. What are the dangers to the spacecraft, and what can we do about it? So for one thing, they took pieces of the spacecraft, that leftover pieces, and they started like throwing things at them at very, very high speeds. This was in a Los Alamos laboratory, and the result is a very, very tiny grain, something the size of a grain of sand, can do tremendous damage at 14 kilometers a second. And that's not good news. So how are we going to deal with that? So the solution was to come up with 3 alternative trajectories. We have what's called nominal trajectory in green. This is how we were planning to fly through the system. But as backup, we made plans for 3 other places where we could pass through the system. The thought being that now we can look at the data as we approach. If we see anything that might be dangerous about the nominal trajectory, we have 3 different alternatives. And that was a huge amount of extra effort planning all of that, but we did it. And so we were ready for just about anything. And then for the about a month and a half prior to the arrival at Pluto, a team of us, about a dozen scientists, experts in image processing and dust dynamics and everything else, were basically pouring through the data as it came down from the spacecraft, just in case there was any sign of anything dangerous in the system. And let me show you again. So as I mentioned, Pluto is in front of Sagittarius. It's in front of a very dense star field. On the left is what our images. These were the satellite images, these were the search images we were using. And this goes back to now January and February of last year. But we were essentially looking at a very, very dense star field with a vastly overexposed Pluto and Charon in the middle. And yet, because these stars stood still, we could subtract them out. And here's the processing that showed the first detections of Nix and Hydra. from these images. These are the same images, but the left is before processing, and the right is after we've subtracted out that star field. So we got pretty good at cleaning up these images. I'll just add a note, since you're astronomers and you know about variable stars. Subtracting out this star field worked beautifully most of the time, but there were a couple variable stars in this star field, and we had so many occasions of false alarms because suddenly there'd be an extra dot in the processing, and that dot was basically because there was a variable star that was suddenly bright that had previously been dim. So the bane of our existence during this whole hazard study was those variable stars that are uncatalogued. Nobody really knows where they are or what they're not that important as stars, but they happen to be close to Pluto as seen from New Horizons. All right, so we went through a good 6 weeks, more than that actually, of this, and this is our last set of images as we're about to approach. This is our last chance. We're 10 days out, actually no, 12 days out. This is our last chance to make a decision to go onto one of those alternative trajectories. By the way, they were called Shabbat, Safe Haven by Other Trajectory. I thought that was a cool acronym. Anyway, so the story is, you probably would have heard about it by now, we didn't find anything. We didn't find any new moons, we didn't find any rings. And so maybe that's a disappointment for somebody like me who studies that stuff, but it was of course really more important as far as I'm concerned just to have a safe flyby. Just to prove that this was an empty field of view, we had lots of test images that we were also doing at the same time, where one piece of our team would make up fake moons, put them into the data, and then it was our job not to just find the real moons, but find the fake ones. And here you can see a smattering of a dozen or so, circled in red, fake moons that we discovered in our processing. So at this point, we're cleared to go. We're going to Pluto, and everybody on the hazard team is pleased and still a little worried because there's always those unknowns. But so now let me sort of shift gears and talk about the Pluto encounter itself, which will be most of my talk. But of course, there was a lot of media attention at this time, and this was a funny email that I got on actually June 30th. It said, "Hi Mark, I'm working for a fun photo op tomorrow with the band Styx, which happens to be touring in the DC area." We had named the moon Styx after the river, not after the rock band, but you know, so it was like, oh my God, I'm actually going to have a photo op with the rock band. This doesn't normally happen to me. This is actually still on the NASA website. You can just Google Styx, you know, Styx meet Styx, and you'll find it. Remember those IQ tests that would say, which of these things is not like the other three? That was my sort of take on this particular opportunity. They're great guys, and they invited us to their concert in Mountain View. They're actually real space buffs. So that was a sort of a fun sidelight for me. It's not the sort of thing that normally happens. But so let's now get to Pluto. Okay, so up until July 3rd, Pluto and Charon could fit inside the Lori field of view at the same time. So here you see a movie sequence. One day, we were essentially getting one image a day. There is so much, it's so slow to get the image down from the spacecraft. So much data has to come down. We only have so much time on the Deep Space Network, which is these big these dishes that collect our data. So one image a day was all we were getting. And this is the sequence then showing a rotating Pluto. This is basically the first time any human has ever seen Pluto as more than a dot in the sky, and it's showing real signs of interesting geology, but we're just getting the hints of it. We know we're going to do better. So now day by day, as we're getting closer, by July 10th, that's 4 days out, we're seeing all kinds of structure. This was a NASA press release with too much information on it. We're seeing, quote, the polygonal structure, which I suspect is mostly a crater. We have the whale's tail. There was a big black area that looked sort of like a whale, and this was the tail of the whale as we were referring to it. And so then, as I said, once a day we would get a new image. And so you'll notice Pluto only rotates takes 6.5 days to rotate. So as a result of that, day by day, we're just seeing a very slight change. And what was really sad to me about the July 11th image is that we're now 3 days out. That means this is the last we're going to see of this side of Pluto. And it looks weird. It's got this thing that I think might be a crater. There's maybe another crater over there. There's like weird lines. There's a bunch of black blotches in the southern hemisphere, but not in the northern hemisphere. Pluto is not just a cratered ball. I mean, I have colleagues who study cratered balls, you know, the moon or Mercury, they're just like cratered balls. I'm not a geologist. I'm sure there are interesting things about cratered balls, but I didn't want to see a cratered ball. And I think Pluto did not let us down. So there's July 11th, July 12th. You see that weird little claw is rotating out of view forever. We're not going to see it again until the next Pluto mission. But we did know by then that there was a big white area that's going to be appearing on the side. And here, July 13th, we're finally seeing some more of that big mysterious white area. And then, ta-da, it's July 14th. This was the last image sent down by the spacecraft before the flyby. July 14th. The spacecraft is on autopilot. The spacecraft is doing its thing. It's executing huge numbers of observations as it flies by in just like a 12 to 20 hour period. It would be foolish to stop halfway through that process, turn and ship data down to Earth. So it's just doing its thing, and we're just holding our breath, waiting to find out whether the spacecraft worked properly for the flyby. So on July 14th, there really wasn't much of any else to do except gawk in that extraordinarily beautiful image, which just shows amazing diversity of structure. I mean, one thing that you might not notice immediately, but you know, I mentioned cratered balls, and you see craters. You see craters all over, up here, over here, over here. This big white area, the heart-shaped area called Tomball Regio, there's not a single crater in there. This is a very young surface. This is like active geology happening, you know, as we speak, which is not something you would necessarily expect for an object that far from the sun. So here we are, just, it was about 5 a.m. in the morning when we were all up to see this image for the first time, release it to the press. It was fun seeing some of the other celebratory and congratulatory notes. We actually got a wonderful recording from Stephen Hawking congratulating the team. We also got the Google Doodle of the day, and here it is. The interesting side note here is that when the Google Doodle appeared, I actually was up sort of late that night and I saw it, and when they first showed it, Pluto was rotating the wrong direction. The heart was coming in from the right rather than from the left, and I tweeted about it. I'm sure I'm not the only one who did, but by morning, Pluto was rotating in the right direction. So anyway, thank you, Google. So we were just waiting until about 9 o'clock that evening for the final official news that the spacecraft had performed properly. All that it did at that point was turn. It was still doing science data, but we decided it had to turn, just send a signal to the Earth that says, I'm okay, I've taken our data or not. And so we got all the telemetry that said, we know we've had a successful flyby, we know it's done hundreds of observations, we know it's put something into the solid state memory that's on the spacecraft, and now we have to wait again. And the reason is that 3 billion miles away, small antenna, there are only 200 watts total budget on the entire spacecraft. That light is shining more power than the entire power budget of the New Horizons spacecraft. And the instrument package, it's about 20 watts. So that's why we haven't seen all of Pluto yet. We're waiting for data to still come down. And it was days we had to wait, but we had a little bit to work with. And of course, now it's 9, 10 months later, so we actually have a lot more to work with. So now let's just look at Pluto. As I mentioned, this is Tomball Regio, the sort of left ventricle of this heart. We call Sputnik Planum. These names are informal, but we are generally expecting them to be approved by the international authorities soon. You can see mountains, you can see interesting, all kinds of structure in here. Craters, you see a big black region, which is Cthulhu Regio, named after a character from H.P. Lovecraft. We had some opportunities to use some interesting names based on our collaborations with the IAU. Let's start with the flyby, or just an animation. One of our colleagues does these exquisite animations where he takes all the data that they've got and just turns it into a flyby. Note, we've got huge contrast. We've got a very, very bright white area, and then off to the side, we've got some very, very dark areas that reflect only less than 10% of the sunlight that hits them, whereas this bright area, it's well over 50%. This is just an extraordinary landscape, and I will do my best now to interpret some aspects of it, although let me acknowledge that I'm not a geologist. I just happen to listen to a lot of geologists talk about this cool stuff. This was another one of our images that I just, this ended up on the cover of Science, I believe. What you can see here, we're looking out now to the limb, and so you can actually get an appreciation for how tall vertically these mountains are. One of the first things they figured out, this is a planet made of ice and various other compounds. It's not a rocky object, it's an icy object. And when you see a mountain, that mountain is an iceberg. Essentially, it's solid ice, because the other compounds that are out there, things like frozen methane, frozen nitrogen, are not strong enough to sustain a mountain. If you made a mountain out of something other than ice, it would just sort of flop down like a souffle or something like that. So you know, those are ice mountains. And you can also see the atmosphere. We knew Pluto had a thin atmosphere. Here you can say that it's got a huge amount of structure, little haze layers made up of very fine dust particles suspended above Pluto. That was also a surprise, because what we assumed or believed was that although there is an atmosphere, it's basically stuff kind of boiling off the surface, and it just kind of floats off into space. But if it just floated off into space, then it wouldn't stop to form haze layers. Excuse me. If you've got haze layers, that means you've got stuff that, excuse me, that's hanging around for a while, that's interacting with other dust particles and so on. So there's a lot more going on in the atmosphere of Pluto than we realized. And in fact, here's a dramatic illustration of that. We got around to the far side of Pluto and looked back, and there's a glint of sunlight shining through the atmosphere all the way around the planet. All right, there is a lot of color information, not in the LORRI data, but in the other instruments. And here's a heavily enhanced version that shows just how much diversity there is on this surface. For example, this is only one half of what we call Tomball Regio, the big heart-shaped region. This is the other half. They're different colors. They're made up of different stuff, even though they look like they go together. Some areas have a very distinct red. This is all very, very enhanced color. It's not what the eye would see, but it gives us a chance to start appreciating the diversity of compounds. On the other hand, Charon, also, by the way, a very interesting object, which I'll talk about in a moment, doesn't have as much color diversity except for that dark region, which is actually right at the North Pole there. And I'll talk about Charon in a moment. Excuse me. All right, so here is one of the other things that we can do with our instrument. We have ways of looking at the infrared light, and certain compounds like methane, which is carbon and 4 hydrogens, glow or absorb at different wavelengths. So by looking at that data, we can actually map out the chemical compositions all over the surface of Pluto. So what we see, for example, is this area we're calling Sputnik Planum is actually got a lot of methane in it, whereas some of the other areas don't. Nitrogen is also heavily concentrated into that area. The Cthulhu, the very dark region, does not have much of that. Here you can see carbon monoxide and how it's distributed. So we essentially have maps of these different compounds across the surface. And of course, we're most interested, just because of its familiarity with H2O, water. And there is not that much water in Sputnik Planum. On the other hand, a lot of these mountains, the ones that I mentioned, had to be made of ice because they're tall, and that's the only thing they could be made of. In fact, they do show up as blue in this region. So here's a close-up showing the boundary between Sputnik Planum and Cthulhu Regio. You see some of the mountains. You see, and you start to appreciate that there's some interesting geology going on here, geophysics, that apparently whatever going on out here, this stuff that isn't water, is actually flowing, because here's a crater that's been filled in by something. And what we've figured out at this point is that nitrogen is, so everything's frozen here, but nitrogen frozen has actually got the consistency of like silly putty, whereas ice frozen at these temperatures, we're talking about 40 Kelvin or so, is rock solid. So essentially, there is flow of the nitrogen, and it's acting like over thousands, millions of years, it's flowing downhill from the planum and filling in things. So you now start to appreciate that there's actually a flow of nitrogen around these icebergs. It's like the mountains used to be taller, and they're being filled in from the sides. And in fact, this is Once again, water ice. This is called a chaotic region. It's sort of like mountains, but it's just a big jumble. But these are essentially floating ice cubes on a sea of liquid, of frozen nitrogen. So silly putty supporting the ice, which is actually a lower density, and so it stays on the top. There's some very subtle but very interesting lines in some of these flows. You can see something going down here and here. And let me show you another view of flows. Just look at all that stuff. If you've ever been to Alaska or seen a glacier, that's what glaciers look like. And so, in fact, these are glaciers. They're not made of water ice the way they are on Earth. They're made of silly putty-like nitrogen flowing downhill and filling things in. So we actually have glaciers on Pluto, although they're not made of water. Here's a close-up of the Sputnik-Planum region, and you can see what's been called the polygonal terrains. There are sort of cells with then boundaries between them. Every now and then you see the tip of a mountain just sticking up. So somehow things have been kind of flowing into this region, gathering in this region. It's very young because there are no craters anywhere in this region. Not a single crater has been seen in Sputnik-Planum. And the idea here is if you ever look at boiling, something boiling, like oatmeal boiling or something like that, essentially, the idea is that you've got heat source from below. You just have rocks, and they have a little bit of radioactivity, so they get a little bit warmer, and that causes an upwelling. So our silly putty-like liquid, solid nitrogen sort of boils up, and then it spreads around, and it goes down. And these are just convection cells. They are essentially the same thing that you see if you boil oatmeal, and is very similar, in fact, to what you see when you boil oatmeal. This took people by surprise because people first started calling it dunes. And the problem is dunes on Earth require wind, and there's not enough atmosphere. There's a little bit of atmosphere, but there's not enough atmosphere in on Pluto to create winds and create dunes. So we've now sort of changed our minds and just called it the bladed terrain, which is sort of non-committal about how it got there. And in fact, we really don't know how it got there, but it's just it's very prevalent in some parts of the surface of Pluto, and my geologist colleagues are still struggling to understand it. There's a lot of interesting substructure inside this big white Tomball regio. Here's stuff we sometimes call this bacilli because it looks a little bit like bacteria. Let me zoom in on that a little bit. And there are things that look almost like fingerprints in here, but and they're linear. In this region, this is linear. These are pits. These are holes in the ground, but they're sort of rounded holes. They don't go too deep. But nevertheless, you can see that there's a whole pattern and structure that's somehow been imposed upon this, and we don't really know the story behind that yet either. All right, now, when we had our closest flyby of Pluto, we did 3 close quick strips of our highest resolution across Pluto. And here I'm going to show you a little animation to help you appreciate that. So essentially, we're as close to Pluto as we're going to get. We take a string of images, and then we string them all together. And so now this is the finest resolution we got on Pluto. What you see in the northern hemisphere is a lot of stuff. It seems like it's basically white stuff laid down on something that's actually much darker. You notice that as the craters go by, there's sort of dark sides and bright sides. It's not precipitation, but it is the idea that you've got an atmosphere, material is moving around, and as a result, you get sort of a frost, a kind of a frost on top of certain things. Now we're in the big Planum area. You see some of these cells of convection, like in your oatmeal. Every now and then you see the peak of a mountain that didn't quite get covered up by the oatmeal, I guess, and as a result, you see little holes there. Just to give you a comparison about the scale, that's the scale we got at Pluto. This is the equivalent scale. I took an image from Google Earth and degraded it to the same resolution. So if we were looking at Earth instead of Pluto, we would see the Golden Gate Bridge. We would see, well, I'm not saying that there's a bridge on Pluto, but we would see the Golden Gate Bridge. We'd see the other bridges. We'd see big barges in the bay. There's Alcatraz. There's the park. We're up there somewhere. So that's just, I hope, gives you a sense of the scale that we're seeing. In just our 3 strips across the planet, that we get the finest resolution. That was all we had time for because we were moving so fast. So here are some of these strips. I'm going to start now, and we'll just scroll through them. Once again, in the north, it's kind of like a layer of frost on top of darker regions. This is getting toward the Cthulhu region that's very dark, and the whiter region on the right is the boundary between the dark region and the big plane. Let me do another one. This is going down across the plane. You can see the crisscross of these boundaries between the cells, some mountains sticking up through the nitrogen sludge, and even some X-shaped features that sort of don't connect up with anything else, but it all suggests this kind of a turmoil, some boiling of the region. All right, now you may have noticed that there are glasses on your chairs. I hope everybody has them. There might be some more in the back if you didn't get one. And I've got a few images to show you that, yes, I will answer that. They will go blue on the right. So if you have not folded, if they've not been folded before, make sure that blue is on the right. All right, so I guess it's actually dark enough outside that I think we'll do okay here. Everybody see that all right? Oops, no, except me. Okay, so we were very careful. One, I'll just say as a side note, it's very, very hard to know which is up and which is down when you're looking at a planetary surface. If you see shadows, that's pretty convincing, but lighting by itself usually isn't enough because it could get dark because there's less sunlight, or it could get dark because it's just dark. And so we were very careful that we did stereo imaging, 2 different viewpoints, like your 2 eyes, of essentially all the area of Pluto that we possibly could. And then we weave that together into these 3D images. So now it's unambiguous what is up and what is down in our images. So blue on the right, hopefully everybody's done that, otherwise your mountains become valleys. Now you can clearly see these mountains are kilometers high. They're actually quite high relative to the small size of the planet itself. You can see the plane is very flat over here as you would expect. There's a big crevice in there. This is just a fascinating geological world with a rich history that we are only beginning to plumb. Does everybody see that okay?
Yosemite Valley.
It's, sure, we'll call it Yosemite Valley. Here's another view. You can definitely see, of course, that the craters go down. That's a good thing. But you also see this sort of windy, it looks like the Grand Canyon to me almost, the way it winds sort of around through things. We are even talking about the idea that there's been flow. Once again, it's not liquid flow, but it's very sludgy, solid flow that has created some of these.
Can you turn off these the lights up here that are
does somebody else want to do that?
scattering on the glasses?
Somebody, I think somebody's trying to do that. Yeah, let's go back and we can get the lights out.
Can you point out that ridge of where it goes way down to the V?
You mean this region?
That way to be at first. Yeah.
What? Yes.
But it goes below that is way deep.
Okay, so let me add a couple things. There has been about a factor of 2 enhancement of the vertical relief.
Yeah.
That's so it's been a little bit exaggerated, just to be clear about that. But I am not a geologist, so I'm not going to speculate. I noticed that this is a fairly flat region but it's not smooth. It's not like this area over here in the plain.
Right.
You know, there's a history. Maybe there was a fracture, and this is something that split apart at some point in the past. There are certainly not tectonics exactly, but there are forces that can break the surface apart and create crevices that way. That may be part of what's going on here. I'm afraid I couldn't tell you. It's a good question, though. I'm sorry I can't say more. So here we have this winding valley system that I said looks a little bit like the Grand Canyon to me. Once again, you get sort of the frosty highlands, where it's not really dark, but it seems to have a bright coating on it. And then a lot of mountains off to the right here. And I think I've got another one. So this is, now you'll see that the pits I mentioned, the bacilli, bacteria, they look like bacteria a little bit, are definitely indentations. They're not, it would not be so clear, except maybe by the lighting, whether these go down or up, but they in fact go down. You see the edge of what may be an old crater here, and the edge of another crater here, or these could be erosional features. The geologists would have more ideas about that, I'm sure. What's striking to me is just how flat this area is. I mean, those are not craters, and there's just not a crater in sight there. And let's now move across this particular terrain. And so we're getting into a very mountainous region. And I wanted to specifically end here because here we have some mountains. Notice particularly this one is a big mountain with a hole in the middle. Now when we look at Earth and we see a mountain with a big hole in the middle, we think volcanoes. And that is actually the working hypothesis about that particular region. So let's more here. You can see once again, would not have been obvious, but the edge of the Cthulhu region, this dark region, actually drops downward as we go toward the plain. And you can now see that here. This is definitely a lower region than the highlands that have the big craters, much older terrain, much darker terrain. So and this is the filled-in crater that I mentioned earlier. So that's what we can do with 3D. And let's see, I think this one moves a little bit as well. Yeah. So here's a much better view of a mountain with a hole in the middle, which, as I said, sure, for anybody who has ever studied volcanoes, they look at this and say, that looks like a volcano. So let me talk about that. Okay, so we are now done with our glasses, and maybe if a few lights can come back on. All right, so here's the image of the, it's not 3D anymore, sorry, but this is, we actually see two of these mountains with holes in the middle. There's one that was well lit, and there's one that was kind of over into the dark side, so it's not much contrast. But our best determinations based on relief is that these two mountains, side by side, 2 miles high, enormous structures, look like volcanoes. Now, there is no flowing lava the way we think. That's melted rock when you're on Earth. The lava, quote unquote, in this case, these are ice volcanoes, as near as we can tell. The one thing that's very distinctive about ice, unlike many other compounds, when you freeze ice, it gets bigger, and that causes ruptures. And if there was something liquid underneath that, it's going to come out through those ruptures. And although this is not geologically active volcanoes, this clearly is a signature that there were volcanoes there in the past on Pluto. Quickly, sure.
What's the color data?
This is relief, I'm sorry. So red is high and blue is low.
And is that radar?
No, this is based on the same principle, stereo imaging. That's how we've got all our relief on Pluto. Okay, so let's, Charon, I haven't said too much about Charon, but it's also quite a fascinating object, about half the size of Pluto. It comes in two halves. It's got a sort of line down the middle, crevices that are very, very deep, and it's somewhat smooth on the bottom with a lot of craters. Actually has about the same number of craters on the top, but it's a much rougher, more of a highlands. And then it's got this dark, probably some kind of deposits at the North Pole, giving it that darker and redder color. When people talk about this region, if you see anything like that on the moon, which you do if you ever look at the moon, we think that's lava flow. That's basically a big mare. But there's nothing like lava in the Charon system or in the Charon body. So we're actually investigating ways that water, frozen water, might have the consistency in such the right circumstances that it flows around and actually acts like it's a flow of lava, even though it's water ice in reality, not melted rock. Let's take another look then at this system, and we're going to do a flyover again. Now we're flying down from the north, which is why that thing is looking, it's actually sort of upside down. We have the canyon that I mentioned. We have a much flatter southern hemisphere than a northern hemisphere. We have this crack down the middle in effect. The belief now, and then we also have, this is essentially what you get if the lava is flowing toward a mountain. It sort of stops when it gets there and it leaves you a kind of a moat. So all this points to something like lava, even though there isn't lava. Let's see, what about that big crevice in the middle? Let me go back and just show that again. It looks extensional. It looks like basically what we think happened is that Charon in the deep distant past kind of inflated a little bit. Now, how would that work? If Charon as it formed, it made a big sphere, but it was hot. And so there was liquid water in the core that eventually, as Charon cooled off, it froze. Ice makes the object bigger because that's why ice cubes float. And so as Charon's crust got thicker because of freezing, the body got bigger and it had nothing to do but expand. And this big crevice that goes all the way around Charon, as far as we can tell, is actually just the sort of growth mark of of Charon at some point in its past. Let me skip over the movie. I hope we can. Okay. Now my four little favorite objects, Styx, Nix, Kerberos, and Hydra. Here we are seeing them actually resolved for the first time. These are objects that were only discovered, a decade earlier, and here we are seeing them resolved, which is kind of amazing. They're all weirdly shaped objects, but that's pretty typical for small moons, that the gravity can't pull them together and make them spheres, so they tend to be lumpy. We clearly see a big crater on Nix there. Here's another view of Nix. This is about our best resolution on Nix. And to me, they are interesting not just because of their weirdo shapes, but because of their dynamics. And among other things we know is that they are spinning in very, very strange ways. When we look at other moons in the solar system, essentially every one we look at keeps one face toward the central planet. The Earth's moon keeps one face toward Earth, as we all know. And that's true of every moon of Saturn except one sort of outlier that's in a weird state. It's true of every moon of Uranus, Neptune, etc. And yet all four of these moons are rotating weirdly. And of course, Hydra is the particularly odd one out. It rotates 89 times every time it goes around the planet. So I am going bonkers. This is my topic, and I'm trying my best to write a paper understanding and describing this dynamics. And you're lucky you caught me on a day when I'm still sane, because I might be over the edge in a few months. Not only are they rotating in a weird way, but they're oriented in a weird way. So here's Nix. It's actually not got its pole. Here are Pluto and Charon that are both, oriented the same way, facing each other. And you've taken Nix and you've sort of flopped it over on its side. And in fact, Hydra, all the moons are kind of flopped over on their sides, as we learn. And the dynamics and history of that remains a mystery that I'm working on. So where do we go from here? Well, here's the Pluto system, and what I want to do is show you, put it in its context. I said there weren't 9, there weren't 10, there were in fact hundreds maybe of planets in our solar system, at least by my reckoning, which isn't the IAU's official reckoning, but that's what I'm saying. The Pluto system is actually sort of the dominant member, the brightest, the closest of a whole swarm of objects called the Kuiper Belt. And that Kuiper Belt is basically made up of primordial stuff, early stuff that got tossed out of the solar system early in the history of our whole planetary system, and has been out there in deep freeze ever since. And we would certainly like to know what some of those other Kuiper Belt objects look like. And in fact, we might get the chance to do that, because after the flyby of Pluto, we did a little tweak to the New Horizons trajectory to target this object. Right now it has the boring name of MU69. Hopefully we'll get a more interesting name eventually. But on New Year's Day 2019, we are going to do a flyby of this object. It's a few tens of kilometers, so it's probably along the sizes of those dinky little moons that I just showed you, but we'll get a much better look at it, and it's a very old, very, very pristine sample of the history of the solar system. So that is only, however, subject to NASA approval. So all we can say is that we're hoping for it. We put in the proposals to NASA for what's called an extended mission that would let us do this extra science as a freebie almost, although of course it does cost money to plan a mission. But we would be doing this over the next couple of years, and New Year's Day 2019 we would have some more great surprises in store. So finally, let me add my little note. Those 3D glasses are not party favors. I do actually need them back. So please leave them on your chairs or in the room when you're done. And I have plenty of time that I'd love to answer questions if you have any. Great. Maybe we can turn up the lights a little bit. Can we turn up the lights a little bit? That way I can see you too. All right, I'm going to start over here.
So, since New Horizons, what do we know about our solar system as a whole that we didn't know before?
I mean, there are so many ways to answer that. We already knew Pluto was there. We knew it was big. We knew it had weird moons. But seeing it as an object that is not a cratered ball, that has active geology, who would have thought that an object 3 billion miles from the sun could actually have an atmosphere, could be recycling, could be having geology, flowing glaciers, all of these things. It just gets you to appreciate that there is a lot more complexity in the outer solar system and in the history of the outer solar system than we might have anticipated until we finally, this is essentially our first look at the Kuiper Belt. We know the terrestrial and the giant planets, so those are the first and second zones, quote unquote, of the solar system. The Kuiper Belt is the third zone. It's like there's a whole new piece of the solar system that we have not yet explored, and we're just getting an inkling that it's a fascinating place. Right here.
Why is it so surprising that the moons could spin? I mean, we're not a moon, but we spin.
Yeah, I mean, it's not that it spins. Of course, everything spins relative to some frame of reference. Yes, but the point is there are gravity forces called tides, and the tidal forces are what has spun down the moon, so that the Earth has tides that it raises on the moon, just as the moon raises tides on the Earth. And the Earth's tides on the moon are enough that it's created friction and slowed it down. And that's why, essentially, as I said, every moon in the solar system keeps one face. That's tidal forces, that's friction, basically does that. These are defying the laws of friction, essentially, by spinning in such weird ways, and that's what we have to understand. Let's go over here in the green shirt.
Is there much change in the, and Pluto in the inner solar system? Are there more forces working on it than there is on the outer edges?
Yeah, so the question is Pluto different when it's closer? Pluto's on a very elliptical orbit, so sometimes it's actually closer to the sun than Neptune, and then at the other times it's much further away. The forces on Pluto, sort of the outside forces, don't really change it very much, except for the part about the sun. And of course, being closer to the sun means you get more heat. So Pluto has a much more extensive atmosphere when it's close to the sun than when it's further away. We're sort of on the tailing end of the atmosphere. As it's cooling off, as it's moving away from the sun, its atmosphere might condense up, onto the surface. But clearly it's still got a very active atmosphere today.
I mean, would that account for some of the features when it's closer in as opposed to
it doesn't really, no, the tides of the sun are not very big. It's essentially, it's going to be the same object, just moved closer to the sun and a little bit warmer. And that's really all that happens. But that's a lot, actually. Let's go to over there, the blue shirt.
Yeah, do you have any thoughts about this supposed Planet X they think they might have found that's supposedly enormous and would be much further out than Pluto?
Yeah, the Planet X, I'm not an expert on that topic, but I tend to be a bit of a skeptic. I don't know, if you look at the history of astronomy, I don't know if you remember there was a story 10 years ago about a star called Nemesis that had passed close to the solar system and created certain events that I think led to the extinction of the dinosaurs or something. There was no Nemesis. It was a great idea, and everybody talked about it for a little while, and it turned out to be hokum. It may well be that this Planet 9 really exists, or Planet X, whatever you want to call it. If it does exist, we will probably know within another decade or two, because it's sort of beyond our capability to detect it right now, but won't be forever. But so in a decade or two, we'll either know it's right or it's wrong. But by that time, if somebody publishes the paper that says, there is no Planet X, it was all hokum, that doesn't get into the news media, and so that's sort of the way science works. The flashy stories get a lot of attention, and the retractions, when they happen, they don't always happen. Sometimes people are right, but don't always get the attention that they warranted.
It helps to be Mike Brown.
It helps to be someone who is very good at doing publicity and public outreach, yes. Mike Brown is a great guy, by the way. Somebody over here? Okay, all the way in the back in the jacket. Brown. Yeah, the composition of Nix. We have, Nix was the one moon of the four small ones that was actually well positioned for New Horizons to do some better observing, and that included some color imaging. It's got some reddish tint around that crater. I did show you a crater, but that's not unusual. Red is just sort of one of those colors that comes up when you take methane or carbon and just sort of irradiate it for a billion years. So we do know that all these objects are mostly water ice, but they have certain other constituents that are going to give them subtle color variations. But from everything we know about them, they're made up mostly of water. Let me, over there.
We're referring to redness. Of course, the redness on shadow all around the North Pole, so that's peculiarity. Maybe something else.
Yes, and my colleagues have a brilliant idea about how that all works, and I can't remember what it is. It has to do with the fact that it's Pluto. I mean, Pluto and Charon you would think would be about the same temperature because, of course, they're both the same distance from the sun. The difference is that Pluto has an atmosphere, so it carries heat around, and Charon does not. And so that region of Charon is incredibly cold. I mean, we're talking 20, 30 degrees Kelvin. And the mere fact that it is such a cold region means that the processes, the chemistry in that region are probably a little bit different. And I am not doing justice to the explanation, so I apologize for that. But it is unique because of its location and its temperature, and that's probably related to why it's darker and different from the rest of Charon. Right here.
How much smaller is Pluto compared to the Earth?
How much smaller? So Pluto is about 2,000 kilometers diameter. Let's see, the moon is, well, Earth is like 6,000. What's the moon? It's a factor of 2 or something like that. I'm not remembering the numbers off the top of my head. Yeah, right here.
I was wondering if you had any comments or opinion on the recent discovery or announcement that most of the water on Earth is from interstellar space, is older than the sun.
I don't know if I've heard that. I mean, the conventional story is that, well, the Earth did not have much water when it first formed, but cometary infall has basically been understood to be the major source of water on Earth.
This was announced from Carnegie.
Yeah, I'm sorry, I'll have to look that up, but I'm not familiar with it. But the conventional wisdom is that, well, there's plenty of ice in the solar system, but not that close to the sun. So when the Earth formed, it was hot and very, very dry. And then there was a period a few hundred billion years later called the late heavy bombardment, when some things happened in the outer solar system. Jupiter sort of stirred things up, and lots of stuff fell into the inner solar system from further out, and there was a lot of comets with a lot of ice, and that's where our water came from. If there's a new story, I'm not aware of it. Sorry. Over here.
Since there are volcanoes, does it mean that it might have a slushy or liquid core, and if so, what temperature?
Which body are you asking about? Pluto. Yeah, so it probably does have a rocky core. There's always going to be a little bit of rock, and that's heavy, so it falls to the middle. That rocky core, by the way, tends to have a little bit of radioactivity, which heats things up. That's why there is probably a liquid ocean of water inside Pluto, and in fact, we know its density, so we know it's got to be there's got to be a lot of water in there. And then as you get higher up, you're further from the heat source, and it's colder, and that's what you get this solid crust on the outside. But as to the actual temperature, it's warm enough for there to be liquid water. So, probably room temperature and even warmer in some close to the core, it probably is quite warm. Over there.
For the Jupiter volcano that you showed us,
Yes.
what's providing the energy at the time?
Oh, in the case of Io, there's a great story, which is that, so the question is about the volcanoes on Io, what's the energy source? There was a paper published in Science magazine saying there should be volcanoes on Io the week before Voyager images showed volcanoes on Io. It's one of the great prediction confirmation stories of all time. The reason for the prediction is that Io is locked So Io is in an orbital configuration with Europa and Ganymede, 2 other moons of Jupiter, and such a way that it keeps Io moving in and out relative to Jupiter. And so Io is the tides that I mentioned. Io has got a big tidal heating. It's being squeezed back and forth by Jupiter's gravity continuously, and that's what gives it a substantial extra heat source, and that has lasted billions of years, and that's why there are volcanoes there. Right back there? Yes, you.
I had a question about that ridge on the chart.
Yeah.
The other thing I noticed, the old chart, saying that they put chart like this.
Okay. Well, that's not your question, but I'll answer that too, but go ahead.
So the question was, you mentioned that at some point they're having like a liquid core. Could that flow that basically above really be at the time that outer shell crack? That liquid core.
Yeah, so the reason that cannot be, so there is liquid core in the middle, but there is never liquid exposed to the vacuum of space, because if you remember your high school chemistry and the triple point of water, there's basically if you go to below a certain pressure, water can only be solid or gas. It cannot be liquid. And in the solar system, you can have water. Same thing on Mars. When they look for water on Mars, they're never looking at the surface of Mars, but down underneath the surface of Mars, there's extra pressure, and that's where liquid water can exist. But by the time you come up to the surface of Mars, there's not enough pressure, and you're below the triple point, and you can either have solid or gas, but not liquid. The other part, pronunciation of Charon. Charon is the boatsman who takes the souls across the river Styx. It's from Greek mythology. If you spell it out in Greek, the first letter is a chi and is pronounced with a hard K. So every Greek scholar, and not that I'm one of those, would say it's pronounced Charon. However, James Christie, who discovered Charon in 1977, I think, decided he wanted to honor his wife, Charlene, so he said, I'm going to call it Charon, because it had to be out of the Greek mythology, but it's going to be pronounced Sharon. That would be like me saying, I don't know, I discovered a moon, I'm calling it Kerberos, but I want it to be pronounced Fred. I mean, it's like, So I philosophically I'm opposed to the idea that the discoverer gets to say how you pronounce the name. They get to choose the name. That's pretty good. But on the other hand, my team members include Alan Stern, who is a real romantic at heart. And he says, if discoverer calls it Sharon, then I'm going to call it Sharon. So I respect that, but I'm not a romantic, I guess.
Speaking of names, the names for Pluto seems to have been labeled as unofficial.
Yes.
For a fairly long time now. The speculation I've seen is that the IAU is being annoyed that there have been some, in their eyes, supposedly frivolous names picked. And that thus the delay in confirming them. Is there any truth to that?
No, actually. So we actually had a naming campaign with their approval, and the names got picked. Maybe they're frivolous in some eyes, but we had permission from the IAU to solicit recommendations. For example, names related to spacecraft, names related to fictional travelers. There's a lot. There's an Oz Terra, fictional locations. There's an Oz Terra on Charon. So we have been very much in keeping with the people's voting, and that was done with the permission of the IAU. Honestly, beyond that, we have not had time. It has been just a marathon since July dealing with this data. We have a database. The channels of communication are open, and we will be meeting with them to we'll put in the formal proposal and all of that. And honestly, it has just been, we followed procedures that they agreed to, and we believe that there's likelihood that they will approve things. If they want to be sticks in the mud, okay, we'll deal with that. But honestly, it's just been of all the things we've got to do, you have a paper that needs to be published next week. You can't submit a name to the IAU and wait 3 months for them to approve it. You just have to say, here's an informal name, we'll deal with the fine work later. But the channels of communication are open. and we're going, actually, the meeting isn't scheduled yet, but there's going to be a meeting probably in Flagstaff, probably in a few months, where we'll be sitting down with IAU representatives and going through all of this. Yeah. Right here.
Is the instruments of the spacecraft tremendously different than what would be launched today? And in other words, what went up there a number of years ago, would it be completely different today?
They are really advanced technology compared to, say, the Voyager era. And they're all designed to be incredibly lightweight, incredibly low power. As I said, 20 watts runs that entire instrument package. So I think if we had to do it today, we would probably use very similar or almost identical instruments. Yeah. We should wrap up pretty soon, so maybe I'll just take one question back there.
I was curious about what the plans of New Horizons are, is this local to get?
Then the team is finished, and there will be a flyby, but there will be no observing going on. I like to think that NASA will see this as an unusual opportunity to see a very, only a second example of a Kuiper Belt object, and will support our proposal, but I cannot speak to that because all I know is we've submitted the proposal and other people are evaluating it. I think the decision will be made in the June timeframe, so we should know pretty soon.
Does it stay there or it's come back?
Sorry, say again?
Come back?
It's on a ballistic trajectory, 14 kilometers a second away from Earth. It's never coming back. All right, I'll be up here if you want to just come forward and we can maybe talk some more. But I want to thank you all. You've been a great audience. I love getting questions like this.